Hello and welcome to Lesson 3.2, Maxima and Minima. So today we're going to first recall what a local maximum or minimum is. When you talk about maxima and minima, you're actually talking about multiple ones. Well, these refer to the values that are the largest or smallest within a small area of the graph or a specified domain. Whereas the term absolute, also sometimes called global maximums or minimums, refer to the largest or smallest values within the entire graph on a specified domain. So let's see what I mean. So let's suppose we're given the following little graph, and as you can see, it's on a specified domain between 0 and 9. Well, what you can do is we can first identify which ones are global maximums and minimums, which ones are local maximums and minimums. Well, first of all, the easiest ones, the highest possible point. So the highest possible point over this entire function on this specified domain is this one. So we call this a global maximum. Smallest point over the entire expression is this one, and therefore is called a global minimum. Well, what you can also notice is these global maximums and minimums. If you just look within the small area, I'm going to draw a little square around the area and a little square around this area. What you'll notice is they are also the highest possible point and lowest possible point within the small area that I've given. So these are also called local maximums and minimums. So you can call them both global and local, and you got to make sure you call them both. While looking at the other points as we go from left to right, the next point at x equal to 2, you can see is a local maximum just within a small area. You can notice the value at x equal to 4 is a local minimum within a small little area. Now this is where the next one comes into play that might be a little confusing. The one at x equal to 9, sometimes it depends on this textbook. Some textbooks say this is nothing. Some other textbooks call this a local minimum. And this one makes more sense to me. This one is a local minimum. It's not the smallest minimum, but it is a local minimum within this small little area given. Now what you can notice is that slope at the local maximum and minimum, and even the absolute maximum and minimums. Well, let's take a look at the slopes of these values of these different functions at the different spots. Well, the ones at the endpoints, this one right here seems to be a positive slope, and the one at the other endpoint seems to be a negative slope. But the slopes on the inside for the local maximums, local minimums, or even absolute maximum, they all seem to be a slope of 0. So it's these endpoints that are a little different from the rest of them on the inside function. So on the inside, the slope of a maximum or minimum of any type is 0. So what this means is if we can find out where our derivative is equal to 0, so notice that these derivatives for this function would equal 0 at each of these spots, then we'll be able to find out most of the local maximums and minimums. The other part is just to find out where on this specified domain. Check those points as well. So this comes now to what we call critical numbers. We therefore define x values where the slope is 0 as critical numbers. We'll also define critical numbers as where the function f of x does not exist and at the endpoints of the function if they exist. So that means for this function up above here, the endpoints and where our derivative was equal to 0 are called critical points. Now the other part of this definition is also when f of x does not exist. This comes into play when we're talking about discontinuity errors and or spots where the function is undefined or just not existing at that spot. Okay. So from this comes what is called the first derivative test for extrema. So suppose let C be a critical number of a polynomial function, f of x, that is continuous on an interval I. If f prime of x changes from positive to negative at the value of C, then we have a local maximum. If f prime of x changes from negative to positive at C, then we have a local minimum. So what does this mean? Well, if we do have a change from positive to negative, that means we have something that's going from increasing to decreasing. So if we have a function like that, you can see clearly it has a local maximum. Whereas if it went from negative to positive, so negative to 0 to positive, then you can see it clearly has a local minimum. Now the only next thing you must do is take all these critical numbers that you have and see if it's the highest possible point for the entire function, and if it does happen, that's an absolute maximum, or if f at c turns out to be the lowest possible value for all the values of x that you can find, then it's a minimum. Now one small addendum to this is if it's just increasing and then it stops, that would be a local maximum or absolute maximum. And if it's just decreasing and then it stops, it's just a local minimum or a global minimum. You just have to check. Okay, so let's take a look at an example. So here we want to classify all the extrema on this function, x cubed minus 6x squared minus 4, on the interval from -1 to 7. So first off, we want to find all our derivative values. So we find our derivative. Here is 3x squared minus 12x. Again, best to find out when it's equal to 0, because if you find out when it's equal to 0, you possibly have some maximums and minimums. This function can be factored into 3x and x minus 4. So that means 3x could equal 0, or x minus 4 could equal 0. So we have two solutions to this. X equals 0 and x equal to 4. Now this is just not enough to actually check if these are maximums and minimums. We also need to know where it's positive and where it's negative. So we need to look at where the function's increasing and decreasing. So we still need to create an interval chart. Now because our domain is specified on from -1 to 7, we have to start at -1 and increase to 0, and then go from 0 to 4, and then go from 4 to 7. Okay, so if I choose a value less than 0, I could choose equal to -1 because it looked like it is equal to that. So if I substitute that in, I'll get a positive value, the meaning the function's increasing here. Choose a value between 0 and 4, plug it in, you'll see that the function's decreasing. Choose a value between 4 and 7, 7 can be included, you'll see it's positive, and therefore increasing. Okay, so as part of this responsibility, not only do you need to know where the function's increasing and decreasing, but you also need to know what the values are at each of these points, at each of the critical numbers. So far we have these two, 0 and 4, as critical numbers. Oops, spelled critical wrong. But we also have -1 and 7 as critical numbers. Because these are our endpoints. So we also need to calculate our critical numbers at -1 and 7. Okay, so let's find these values out. So this one's -11, this one's -4. Just gotta grab my calculator here to work out my other values. This one's -36, and let me figure out my last value. And 45. Okay, so what you can see clearly, the biggest number is 45. So therefore the point 7 and 45 is a global. Now remember, it could also be the smallest possible, be a local maximum. Lowest possible point is -36, so 4 and -36 is both a global and a local minimum. Well, because the function is increasing after the value of -1, we know the value -1 and -11 is a local minimum. And the value at 0 and negative 4, well, 0 and negative 4 goes from increasing to decreasing. So what you can see right there, 0 to negative 4, is a local maximum. Now with this information, you could actually draw what this function looks like with a pretty good accuracy. And thus concludes this lesson.